Hello students, this is Professor Chalai, and in this video we're going to look at phase transitions. As always, you can follow along with our Chapter 10 workbook. By the end of this video, you should be able to define what a phase transition is. You should be able to explain the relationships between phase transition temperatures and intermolecular forces, and you should be able to compute enthalpy changes associated with various phase changes. Let's get started. Now, this video is going to be long because I plan to cover sort of vaporization, condensation, and vapor pressure. I also intend to cover the Classius-Clapeyron equation, and I also intend to cover the enthalpy of various phase changes. Feel free to pause the video at any point and take a break, and come back to it later. I'll see if I can film this all in one go. Odds are I'll probably won't be able to, or if I do manage to get it all in one take, I'll probably stumble over a lot of words. So we'll see what happens. Okay, so what do we mean by phase transitions? Simply put, phase transitions, and it looks like I didn't put a little definition box for that, but a phase transition is simply a fancy way to say that you're changing from your state of matter. So you're changing the physical state of matter. So if you have ice melting, right, it's going from a solid to a liquid, that's a phase transition. Something evaporating, that's a phase transition going from the liquid to the gas state. So in this section, we're just going to look at various phase transitions and look at what causes them and the energy changes associated with them. Now, in our chapter on gases, we talk about this idea of vapor pressure. I'll leave dynamic equilibrium for you to sort of research on your own, but let's look at vapor pressure. We talked about how vapor pressure was the pressure of the gas right above the liquid phase, right? So it's the pressure of a gas above its liquid phase. Now, why is there always some amount of gas above its liquid phase? Well, when we looked at gases, we said that even though the average temperature in the air might be a certain degree Celsius, for example, that doesn't mean that all of the air molecules are moving with the same amount of energy at the same speed. They all have a range of speeds, right? And then we know that speeds or velocity is related to kinetic energy. So the same it is for liquids, right? Liquids at any single temperature, all of the liquid molecules are not moving at the same speed. They don't have the same kinetic energy. In fact, they have a range of kinetic energy similar to gases, right? Now, similar to gases, if it's at a higher temperature, right, the average kinetic energy will be higher than if it was at a lower temperature. Now, all of the all of the liquid molecules, right, we said are held together by these intermolecular forces, but if there's some molecules that are moving so fast and have so much kinetic energy that they're able to break these bonds, they can escape as a gas. So this is the liquid, and that's the gas. And so if all sort of liquids have a range of temperature, I'm highlighting the range of temperature here, then there is some minimum temperature that they require to break, or rather minimum kinetic energy that they require to break their intermolecular forces and escape into the gas phase. And so at any point in time, there's going to be a little bit of amount of molecules that have enough temperature to escape. And so that's why we always have a vapor pressure. Regardless of what temperature you have your liquid, there's just going to be a tiny amount of liquid that has enough energy to escape and become a gas. Of course, the higher your temperature, right, let's use red for this higher temperature, the more liquid would have energy to escape. If your temperature is lower, like here, you'll have fewer molecules that are able to escape because they have enough kinetic energy. Okay, and so the amount of energy that they need, though, to break free is dependent on the intermolecular forces. If the forces are stronger, you need more energy to break free, and so your vapor pressure will be lower because not enough molecules have the temperature to break free. So with that, let's look at number 9. Here it gives us 1, 2, 3, 4 different molecules, and it's asking us whether their vapor pressure, what their relative vapor pressures are. Which ones have lower vapor pressures, which one would have higher vapor pressure, as determined from their intermolecular forces. So let's first look at all of them and try to figure out what their intermolecular forces are, and therefore which ones will have the lower or higher vapor pressure. So let's look at ethanol. Ethanol, everything has dispersion. So let's put dispersion up there. Ethanol has oxygen. It'll form a dipole moment, so it'll have dipole-dipole interaction. Dipole. So let's start to write this all using shorthand. Dispersion, dipole, dipole. It has a hydrogen bonded to an oxygen, so that it has hydrogen bonding, so H bonding. There are no ions in there, so it doesn't have ion dipole interactions. What about ethylene glycol? Well, it has dispersion because everything does. It has dipole-dipole interactions because the oxygens there will allow for dipoles to form, and it has H bonding as well. Recognize though that one, this is a larger molecule, and so its dispersion would be larger. And two, it has two different hydrogens for hydrogen bonding. So let's put a ×2 right there for hydrogen bonding. Two available hydrogens for hydrogen bonding. Okay, let's look at diethyl ether, right? What do we have? It has dispersion, because everything has, and it's pretty large dispersion, but again, dispersion is the weakest of the set, so we'll see what else it has. Dipole-dipole interactions, because we know this oxygen will pull electrons to itself, and this geometry is bent, even though it's drawn as a straight line here. There'll be two lone pairs on that oxygen that makes it bent, so it will have a dipole-dipole interaction as well. But it has no hydrogen bonding. There are no hydrogens bonded to this oxygen, so no hydrogen bonding. And let's look at water. Water has dispersion, but just a little, because it's a small molecule. It has dipole-dipole interactions, and it has hydrogen bonding, and it has two hydrogens available for hydrogen bonding, so let's put a ×2 there. So if we were to order this in terms of weakest to strongest intermolecular forces, so let's use this. For the intermolecular forces strength, right, the weakest here would be diethyl ether, right? Diethyl ether. You know what, to make this faster, I'll just label these A, B, C, and D. A, B, C, and D. So for intermolecular forces, C here will be the weakest. Then what do we have? Both ethylene glycol and water has two hydrogens for hydrogen bonding, and that's the strongest one, whereas ethanol only has one hydrogen bond, so A will be next up. Then we have water, because water and ethylene glycol have the same sort of hydrogen bond and dipole-dipole sort of ability, but water has a weaker dispersion, so we'll put water next, and then ethylene glycol after that. So if we're talking about vapor pressure, right, the one with the strongest intermolecular forces will have fewer molecules that have enough energy to escape if they're all at the same temperature. And so that one will have the lowest vapor pressure. So for the vapor pressure, it'll be the opposite of the intermolecular forces. The lowest vapor pressure will come from B, which is ethylene glycol, followed by D, followed by A, followed by C. Did I get that right? Yep. Okay. So that's just one way to think about vapor pressure and intermolecular forces. The stronger the intermolecular forces, the weaker the vapor pressure. All right. Try number 10 on your own and try to do the same reasoning for, well, try to answer number 10 on your own. Okay, so let's look at number 10. We have a certain temperature, so they're all at the same temperature, which means that the average kinetic energy, well, they're all at the same temperature. The question is asking us, explain the various different vapor pressures. So let's look at each of these. And the easiest way to try to figure out what are all their different intermolecular forces is just to look at their structures. So methanol, again, I'll just label these A, B, C, and D just to make it faster. Methanol has a structure like this, and then an OH, well, right, that's A. B They all have very similar structures. It might not be worth it to draw all of their structures. Yeah, it's not worth to draw all their structures because the idea is the same, right? They all have sort of this OH group attached to this carbon-hydrogen framework, which you'll learn a lot more about once you get to organic chemistry. But the only thing that's different is their sizes increase, right? This one has 1 carbon with hydrogens, this has 2 carbon with hydrogens, and this has 3 and 4. So the only thing that's different is their number of carbons. So based off of this, it looks like they should all have dispersion. They should all have dipole-dipole interactions because of the oxygen. And they should all have hydrogen bonding with 1 hydrogen available for hydrogen bonding. However, in A, the dispersion is weak because it's a smaller molecule, and D, the dispersion is strong because it's a larger molecule. And so it makes sense that as you go down this table, the dispersion gets higher, stronger and stronger, and therefore the intermolecular forces get stronger and stronger. Therefore, the vapor pressure gets lower and lower because fewer and fewer molecules would have enough energy to escape. Okay, so we talked about vapor pressure being the ability, well, it comes from the fact that some molecules will always have enough energy to escape into the vapor phase because they have a range of energy. The boiling point of a liquid comes when the vapor pressure, so it happens when the vapor pressure is equal to the atmospheric pressure. So boiling happens when vapor pressure is equal to atmospheric pressure. So in this table here, it shows how vapor pressures for a few different liquids change with temperature. We know that if you increase the temperature, right, you're giving more energy to the molecules and more of them will have enough energy to escape. And so the vapor pressure keeps going up as you add more heat. Atmospheric pressure is about 101 kilopascals, right? So here it shows that for ethyl ether, sorry, as you increase the temperature, the vapor pressure increases until at some point the pressure is equal to atmospheric pressure. So let's put atmospheric pressure. And that's atmospheric pressure at sea level. And the point at which the atmospheric pressure the vapor pressure is equal to atmospheric pressure, that temperature that occurs at, that's the boiling point of that liquid. So if we look at the example here for water, which is in blue, because why not? Water is blue. The temperature at which the vapor pressure of water is equal to the atmospheric pressure is 100 degrees Celsius. And that's how that works. So if we were to look at, try to analyze this graph using number 11, for example, it says that the atmospheric pressure in Leadville, Colorado, which is about 10,000 feet up, is 68 kilopascals. So what would be the boiling temperature, boiling point of water at that elevation? Well, we look at 68 kilopascals, which in this graph, I don't know, I'll say it's probably there, right? Then the temperature of water looks to be around 90 or so degrees Celsius. So I would say about 90 degrees Celsius. All right, try to answer number 12 on your own using that graph. Okay, let's look at number 12. It says that the boiling point of ethyl ether was measured to be 10 degrees Celsius at the base slope of Mount Everest. So what's the pressure there? So let's go up to this graph. Let's figure out where 10 degrees Celsius is. Might be here. If you go across here, that pressure, this is just a graph, so we have to estimate. But I would say that might be, I don't know, 35 kilopascals or so for pressure. So I will say around 35 kilopascals. So you might be wondering, we have this graph that tells us how the vapor pressure changes with temperature, but it's all very guesswork, right? Like we just sort of draw lines. Is there an equation? We know that for lines there are equations. So is there an equation for us to accurately figure out what the vapor pressure and temperature relationships are? is there, it's clearly not a straight line. It's not a y is equal to mx plus b line, but surely there must be some curve that we could fit here so that we could figure out these with a little bit more accuracy than just like guessing. And if you're thinking ahead, you're looking ahead, the answer is yes, there is an equation to that line, those lines, an approximation that we can use to figure out how the pressure and temperature are related. And that equation is called the Classius-Clapeyron equation. This curve, as we mentioned, is not a straight line, but it sort of grows like this. It's an exponential. So we can use an exponential to describe that line, and so this is what we get. P here, according to that graph, is y on the y-axis, and temperature was on sort of the x-axis, so P grows as an exponential of the temperature. In this equation, let's erase some stuff. P is the pressure, as we mentioned. A is just a constant. The exponential, this here, delta H of vaporization, is the enthalpy of vaporization. And we'll talk about this in a little while, but it's the enthalpy change for a reaction when you go from the liquid phase to a gas phase. So for example, in water, if you go from H2O liquid to H2O gas, the enthalpy for that reaction will be the enthalpy of vaporization. You're vaporizing the liquid. So as all most enthalpy reactions, this is usually written in terms of kilojoules per mole. Let me write using a different color. Usually written in terms of kilojoules per mole, but to make all of the terms come out nicely, we'll just use joules per mole, right? R here is the ideal gas constant, and we're going to use the energy form of it, 8.314 joules per mole per Kelvin, instead of the liters times atmosphere version. And then T here is the temperature, and as because this is in Kelvin, temperature needs to be in Kelvin. Okay, so in this equation, we can figure out how pressure and temperature are all related to each other. Now, what happens if we want to figure out how pressure and temperature changes are sort of related to each other? Well, let's do some derivation. If you want, you can sort of skip ahead to this next part and just use this 2-point formula in your calculations. But if you'd like to see how we get that, well, just stick around for a little while. So we know that the pressure is equal to this constant times an exponential of minus delta H of vaporization over, wait, I already forgot what it was, over R times T. Okay, now we know that A is a constant, so let's put all of the constants to one side of the equation. So we'll get P times, we're dividing by an exponential, but for exponentials, right, if I'm dividing by e to the minus whatever, it's the same as multiplying by e to the positive, the same thing, right? So e to the power of positive delta H of vaporization over RT, right? So instead of dividing by a negative and multiplying by a positive exponential, it's the same math. So all of that is equal to the constant A. Now, we did this same thing with gases. When if something's equal to a constant, then that constant by its nature doesn't change from the beginning to the end of the experiment. So if we say that this is the pressure and temperature at the beginning of the experiment, let's call it P1 and T1 for the beginning of the experiment, that's going to equal to P2 times E to the same heat of vaporization over R times T2 at the end of the experiment, right? So then we can set these two things equal to each other. P1 times E to the delta H of vaporization over R times T1 is equal to P2 times E to the delta H of vaporization over R times T2. Let's put pressure on one side and everything else on the other. So this is P2. We'll keep we'll put pressure on the right and keep everything else on the left. So if we divide by pressure here, we get that. We can divide by the exponential, right? Like this, over RT2. We talked about how dividing by an exponential is the same as multiplying by the negative of the exponential. So let's, instead of doing that, let's multiply by negative of delta H vaporization over R times T2. Okay, so let's simplify this further. So we have P2 over P1, right, from here, is equal to, we have two exponentials multiplied by each other, so this all comes out to delta H of vaporization over R times T1, right, this is the positive one here, minus delta H of vaporization over R times T2. Let's see if we can simplify this further. Up here, delta H of vaporization and R is in both of them. So we can simplify this as, let's write that again, P2 over P1 is equal to E to the delta H of vaporization over R. And then we have 1 over T1, right, for this T1, minus 1 over T2 for T2 here. We're not done yet because lots of people don't like exponentials in their equation. So let's do the natural log on both sides. So we'll have natural log of P2 over P1 on the left-hand side, and on the right-hand side, the natural log cancels out the exponential, and we have delta H of vaporization over R into 1 minus T1 over 1 divided by T2. This is the 2-point form. Spent a long time getting there, but we use this 2-point form when we want to figure out how the pressure or temperature changes. How the vapor pressure, P is a vapor pressure, let's specify vapor pressure. In the end, P1 is vapor pressure in the beginning, T1 is the temperature in the beginning, T2 is the temperature at the end. So if you knew any three of those, you can find the fourth one. Or if you knew all four of these, you can find what the enthalpy of vaporization would be for that liquid. So with all that done, let's do one for practice. And there's a few more that you can pause and do by yourself. So let's start with number 13. So number 13, we have isooctane, has an octane rating of 100. Again, that part is irrelevant to the question, it's just giving you some information. It's a standard for octane rating system for gasoline. At 34.0 degrees Celsius, it gives us the vapor pressure. So we'll call that temperature T1, 34.0 degrees Celsius. However, we know that temperature must be in Kelvin, so add 273.15, and that temperature comes out to be, there we go, 307.2 kelvins, right? The pressure at that temperature is 10.0 kilopascals, right? So that's T1 and P1. Notice I'm not going to convert kilopascals to atmospheres because in this equation that we're about to use, pressure will divide by pressure, giving us a unitless quantity to take the natural log of. Okay, so we have T1 and P1. What else do we have? It says at another temperature, so let's call that T2, it's 98.8 degrees Celsius, but we need this in Kelvin. So that should be 372.0 Kelvin. It gives us the vapor pressure, P2. Yeah, we'll use a different color. Colors are nice. Let's use orange. P2 at that temperature is 100.0 kilopascals. They want us to use this to figure out the enthalpy of vaporization. So we have all four of these quantities. They want us to figure out what the enthalpy of vaporization is. So let's set up this equation to solve for the enthalpy of vaporization, right? It's the Classius-Clapeyron equation, but we'll use the 2-point form. Let's see if I remember how to write it. It's natural log of P2 over P1 is equal to the enthalpy of vaporization divided by R times 1 over T1 minus 1 over T2. Now we want to solve for delta H of vaporization. So I'm going to rewrite this equation to solve for that. But how am I going to do that? Well, let's take everything else on the left-hand side that's not the enthalpy of vaporization. So we multiply both sides by R, and then we'll have to divide both sides by this whole thing. So it's divided by 1 over T1 minus 1 over T2. Well, that wasn't as hard as I thought. There it is. Note that we couldn't just like subtract out or flip these T temperatures, even though we're dividing by it. We're dividing by the entire thing. And so be careful with your algebra when we're using that. So now we have the delta H of vaporization. All we have to do, let's rewrite it. It's equal to R times the natural log of P2 over P1 divided by 1 over T1 minus 1 over T2. I would save this equation in a nice place because we're probably going to use it again, and you don't want to derive it over and over again for the heat of vaporization. So at this point, it's all just plugging numbers in, right? So if I do, oh, I'm going to run out of space, aren't I? Okay, let's move this in. Let's move this over just a smidge so that we have some space to work with. Okay. There we go. No biggie. All right, the heat of vaporization is equal to R. R we know should be 8.314 joules over moles times Kelvin. Okay, then we're doing the natural log. So this is all multiplied by the natural log of P2, which happens to be 100.0 kilopascals over P1, which is 10.0 kilopascals. Of course, as I mentioned, the kilopascals will cancel out. So we're taking the natural log of a unitless quantity, as you always should, at least in this course. And then it's 1 over T1. So it's 1 divided by, I already forgot what T1 was, 307.2 kelvins. Minus 1 over T2. T2 was 372.0 kelvins. Unit cancellation time. Kelvins, 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 right? It's in the denominator up here, denominator down here. That's why I'm able to cancel this one with both of these. Well, that's sad. That's the only thing that cancels. Okay. All right. I mean, as it should. So now it's time to plug numbers in your calculator. Now here's, I think that's something that's very important. When you're doing this denominator here, make sure to put everything like that in parentheses. Some calculators, you're not sure what it's doing with those denominators. So just put them in extra parentheses. Nothing, it can't hurt anything. Okay, so the enthalpy of vaporization, our units will be joules over moles, right? That's what's left over there. Plug all of this in my calculator, and I got 33760 joules over moles. Now, enthalpy of vaporization, as I mentioned, usually is measured in kilojoules per mole. So it's just 33.76 kilojoules per mole. 4 sig figs. I want you to look at how you deal with significant figures in logs. Actually, I'll tell you instead of having you go search for it. So if I were to divide this, right, we will get 3 sig figs for the answer. 1, 2, 3 here, 4 up here. So we'll get 3 sig figs for the stuff inside the parentheses. When you take, let's create some space. Sig figs in logs. Okay, so we had log, or natural log in this case, natural log of 10.0, right? That's the 3 sig figs when we're done with it. So we have 1, 2, 3 sig figs. So let's put 3 sig figs. When you take the natural log of a number, that number of sig figs become the number of sig figs in the decimal place of your answer. So if I get the natural log of 10.0, you know what? I'm going to take not the natural log. I'm going to take log base 10 because I know how to do that, what number in my head. Log base 10 of 10.0 is basically 2.0000, right? But we have 3 sig figs here, so we need 3 sig figs in the decimal place. So that would be our answer. So while it's 3 sig figs in the decimal place, it becomes 4 sig figs overall. The opposite happens when we do the opposite of logs. So the opposite of logs would be exponential. So let's say we're taking the exponential of, I don't know, minus 8.32, whatever. Let's look at that number. Here, we do the opposite. We count the sig figs in the decimal place, right? So let me just reiterate 3 sig figs to 3 sig figs in decimal place. So it becomes 4 sig figs overall. Here, we do the opposite. We count sig figs in the decimal place. 2 sig figs in the decimal place should become 2 sig figs overall. So 2 sig figs in decimal place should become 2 sig figs overall. And so if I punch this number in my calculator, I get something like 2.4 by 10 to the negative 4. Here's my 2 sig figs. So logs and exponentials work a little bit differently than subtraction and addition or multiplication and division when it comes to significant figures. We go from counting the total sig figs to putting that in the decimal place when we go from logs to regular number. And then we do the opposite when we go from exponential to writing the number full out. We go from counting the number of decimal places to being that's entirely what our number of sig figs should be. So here we went from total of sort of 3 sig figs to only 2 sig figs in the answer, right? Because the number of sig figs changed. So that is why I ended up with 4 significant figures here, because up here, while this number here gave me 3 significant figures, when I take the natural log of it, I got 4 significant figures, and then everything else is 4 significant figures. Seems like a lot, I know. You can rewind that and watch what I did again. But let's try to answer number 14 on your own. So number 14, it tells us that at some temperature, we'll call it T1, it's 20.0 degrees Celsius. Again, we need this in Kelvin. So that's 293.2 Kelvin, right? It tells us that the pressure, so that's the first pressure, is 5.95 kilopascals. And then at some other temperature, I'm going to run out of space again, aren't I? So let me start by shifting this down. Whoops. I'm not going to edit this out because I anticipate this is going to be a very long video. So you'll see some bloopers along the way. There we go. Okay. Then at a new temperature, T2 at 63.5 degrees Celsius, which is in Kelvin, 336.7 Kelvin. Again, if any of my numbers are wrong, please let me know. But yeah, it tells us that the pressure at that new temperature is 53.3 kilopascals. 53.3 kilopascals. Same thing, it wants us to estimate the enthalpy of vaporization using this setup. Now, we already have the equation up here, so I'm not going to write that equation again, or derive the equation again, because it's right there. So we know that delta H of vaporization will be R, which is 8.314 joules per mole per Kelvin, multiplied by natural log of P2, which is 53.3 kilopascals, divided by P1, which was 5.92 kilopascals. Kilopascals cancel out. In the denominator, we have 1 over T1, which was 293.2 kelvins minus 1 over T2, which was 336.7 kelvins, time 4 unit cancellation. Well, that was boring last time too, wasn't it? Because we only had the 1. So delta H of vaporization in joules per mole happens to be, remember, put parentheses around these things and try to punch it in your calculator. Make sure you can get the same numbers. Understand how your calculator works for divisions and exponents and natural logs. Make sure you know where to find natural logs and exponents and all that in your calculator, because here's when it starts becoming useful. This comes out to be 41460 joules per mole, or 41.46 kilojoules per mole. 3 sig figs up here becomes 4 sig figs in our answer, and then these are all 4 sig figs. Okay, how about number 15? Not asking for the same thing, but it's asking for the new boiling point. Try to do this one on your own. It's a little bit different. Try to do it on your own, and then you can unpause and we'll do it together. Okay, so we're going to do the same thing. Like all of the questions, we've been writing what they give us first. So we have a normal boiling point of 80.1 degrees Celsius. So that's one of the temperatures, 80.1. We want this in kelvins, which is 353.3 kelvins. The normal boiling point, what is the vapor pressure at the normal boiling point? It's the atmospheric pressure, which I said earlier was 101 kilopascals. Or 1 atmospheres, and you can convert it to pascals or kilopascals on your own. Okay, so we have that first information. We have T1 and P1. P1 just came from this statement of a normal boiling point. Okay, let's see what else we have. We have the enthalpy of vaporization. So they give us this one. It's 30.8 kilojoules per mole, but in the equation it should be joules per mole. So we just multiply it by 1,000 joules per mole. Okay, and they wanted us to figure out the boiling point in Denver. I am assuming Denver, Colorado. There might be other Denvers, who knows. Where the atmospheric pressure, so that's the new pressure, P2, is 83.4 kilopascals. They want us to figure out what's the new, what's the temperature at that vapor pressure. So here we're going to use, why do I always have to end up creating more space? Actually, I maybe have enough space. Let's see. Okay, so let's set up our equation, and now we need to solve for T2. So we know that natural log of P2 over P1 is equal to, I forgot what it was. Here it is. Here it is. The heat of vaporization over R over, let's erase that, 1 over T1 minus 1 over T2. We're solving for T2, right? So we need to rearrange this equation to, to solve for T2. How do we do that? Well, let's see. See, I knew I was going to need a little bit more space because I never give myself enough. Let's move all of this. It's not letting me. Or is it letting me? It is letting me. There we go. This is what you get unedited. See all the stuff I have to edit out usually. Okay. So I made myself more space. So I'm trying to rewrite this equation to solve for T2. Now you can punch numbers in your calculator and try to solve for T2 your own way. It's all algebra at this point. It depends on how comfortable you are with various types of algebra. But for me, to solve for T2, I'll put everything else on the left-hand side. So I'll multiply both sides by R, divide both sides by this delta H of vaporization. So that gets rid of those. And then I'm left with 1 over T1 minus 1 over T2. So if I subtract 1 over T1 on this side, right, we'll get minus 1 over T2. So if I multiply everything by minus 1, this becomes a positive sign, and then this becomes a negative sign. Again, if you're not sure what I'm doing, just slow it down a little bit. You'll see what I just did. I basically had a negative 1 over T2 over here. And so to make it positive, I multiply by everything by minus 1. So the minus sign here became positive, the positive sign here became negative. And then it's 1 over T2. I need just regular old T2, so I need to flip it, right? So if I flip it, I get T2 on the right-hand side, and then on the left-hand side, let's use a different color, I get 1 divided by all of this stuff, right? So it would be 1 divided by 1 over T1 minus R times natural log of P2 over P1 divided by the delta H of vaporization. Seems like a lot of work, but now we have an expression for T2, which we can just plug into a calculator. If you want, you can go ahead and sort of save that so you don't have to derive it ever again. Okay, so now I'm going to plug numbers into a calculator because, well, I'll write the numbers down first and then plug it in, so I know I'm not missing anything. T1 was 353.3 kelvins. 353.3 kelvins minus R. Yep, R is 8.314 joules per mole per Kelvin times the natural log of P2 over P1. P2 happened to be 83.4 kilopascals divided by P1 was 101 kilopascals. It was regular at all atmospheric pressure. All of this divided by the heat of vaporization, which they told us was 30.8 kilojoules per mole, but we want that in regular old joules per mole, so it's 30800. So 30800 joules per mole. All right, let's see what cancels with what. Moles will cancel with moles, joules with joules, kilopascal with kilopascal, and that's a natural log anyway. So we plug all of these numbers into our calculator. Make sure you put parentheses around things that should have parentheses, makes it a little bit easier. Like you can even put a parentheses over there when you're doing calculator. In fact, you'll probably want one big parentheses. Let's use a different color so you see this new parenthesis. These one big one around everything in the denominator. Just calculators work weird sometimes. You need to understand how yours work. Okay. If I punch all of this into my calculator, I believe my units will be kelvins, right? It's in the denominator, so it will be the numerator. And I believe I get 347 kelvins, 0.0 kelvins. You can verify my answer, let me know if I'm correct, but if you convert that to degrees Celsius by subtracting 273.15, I get, converted to Celsius, sorry, I get 73.8 degrees Celsius. And the last thing you want to do with every question is just make sure that makes sense, right? Let's read the question. The normal boiling point is 80.1 degrees Celsius, and you move to a higher elevation where the pressure is lower, so the boiling point should get lower, and that is what we did get in our answer. 73.8 is lower than 80 degrees Celsius, so our boiling point was lowered. And so number 16. So far I haven't taken a break yet. This is going well. I don't know how long this recording is. We'll see. All right, for acetone, the normal boiling point is 56.5 degrees Celsius. So that's the first temperature, 56.5. But again, we want this in Kelvin. This comes out to be 329.7 Kelvin. Normal boiling point means that the pressure is atmospheric pressure, 101 kilopascals. Okay, what else we have? The enthalpy of vaporization, okay. The enthalpy of vaporization is 31.3 kilojoules per mole, or 31300 joules per mole, which is what we'll use in the equation. Down here it says what's the vapor pressure of acetone at 25 degrees Celsius, so that's our new temperature, 25.0 degrees Celsius, but we want that in kelvins, so that comes out to be 298.2 kelvins. Okay, so it's the same type of equation. Wait, no, not the same kind of equation. We're searching for P2 now. So we want to know what P2 is. So let's do the same thing we've been doing. We take the original equation, natural log of P2 over P1 is equal to the enthalpy of vaporization over R divided by 1 over T1 minus 1 over T2. Now we need to solve for P2. Now, when you're dividing natural logs, that's the same as subtracting them, right? So let's erase this, and that'll be the same as natural log of P2 minus natural log of P1. Right? So all I did was separate that out. P1 was in the denominator. I did that because I want to separate P2 from P1 because we're trying to solve for P2. So let's put everything that's not P2 on the other side. So we add this on the other side. And so we have natural log of P2 on one side and then everything else on the other. Now, to get rid of the natural log, you take the exponent, right? So the exponent of a natural log is just the number. So e to the natural log of P2 just becomes P2. This becomes e to the delta H of vaporization over R times 1 over T1 minus 1 over T2, right? And this becomes e to the the exponent of a natural log just becomes P1. And this plus sign is now a multiplication sign. If you want to figure out how I did that, let's just call all of this stuff here A, and this P1, and yeah, let's just call all of that stuff A. So we have A times the natural log of P1, and we were taking the exponent of all of this, right? So that will be equal to the exponent of A, A plus natural log of P1, not multiply, because there's a plus here. All right. So if we did that, it's the same as taking e to the a times e to the natural log of P1, right? And so this part here just becomes P1. So we got e to the a multiplied by, what's wrong with my computer? There we go, multiplied by P1. And so that's how I ended up with this situation. E to the that stuff multiplied by P1. Essentially that positive sign changed to a multiplication sign. It's okay if you're not comfortable with logs and exponentials. Just do some for practice. I'm sure we all did it in high school. It might just been a while. All right, so now we have an expression for P2, and again, you might want to just highlight this so that if you need to use it in the future, you don't have to derive it all over again. Now that we have it, all we got to do is plug numbers in, right? The delta H of vaporization, they tell us, was 31300 joules per mole. So, hang on, this should all be in an exponential. So let's make sure we put the E there for the exponential. So it's all of this divided by R, which is 8.314 joules per mole per Kelvin. There we go. I was struggling to remember what units were there for a second. All of this multiplying by 1 over T1, which was 329.7 kelvins, minus 1 over T2, which was 298.2 Kelvin. Yep, that's all the exponentials. And then I'm multiplying this by P1, which was 101 kilopascals. Okay, unit cancellation time. Let's see, joules, joules, moles, moles, Kelvin, Kelvin, Kelvin. Well, that was easy. And this also sort of makes sense. We're taking an exponential, so everything, at least in this course, everything in all the units in that exponential should cancel out, because what if you had, I don't know, let's say you had Kelvin, like 7 Kelvin. If you take the exponential of 7 Kelvin, what's the new unit that you get? We haven't touched that yet, and we won't in this course. So when you're taking logs or exponentials, all of the units should cancel out. And so the units that we're going to be left with is just going to be kilopascals, which makes sense because this is pressure. I plug all of this in my calculator. Remember, put parentheses to help you along everywhere that you need to, right? But if I plug this in my calculator, I get, I believe, 30.2 kilopascals. I may have punched things wrong, but let's see if this even makes sense. So the temperature was 56.5 degrees Celsius, the normal boiling temperature. And the question is, if we lower the temperature, then the vapor pressure should be not atmospheric pressure, but lower than atmospheric pressure, and 30.2 is lower than 101. So it sort of makes some sense. Whether or not it's accurate, we'll see. Okay, so that's all using the Classius-Clapeyron equation. It's an exponential equation or a log equation, depending on which form you use. And it can feel a little bit tricky. Just practice using logs, and we've derived a few different forms for it. The form to solve for the enthalpy of vaporization, a form to solve for the final temperature here, and a form to solve for the final pressure here. So those are really the only three things that we'll ever try to solve for. So there shouldn't be any other, I don't think there's any other things you need to solve for. But if you do, just let me know and we can go over that together too. Okay, so we talked about this idea of vapor pressure. It happens because some molecules always have enough energy to escape into the gas phase. We talked about how there's an enthalpy of vaporization all the way up somewhere here, where it's really the enthalpy of the reaction as it goes from liquid to a gas. In fact, there are many different phase changes with associated enthalpies. So enthalpy of vaporization, I'm just going to give an example for all of these. I give the example of water going from a liquid to a gas, and that's the enthalpy of the reaction, enthalpy of vaporization. The enthalpy of condensation is the opposite, right? So vaporization, this will usually be endothermic, because you need to add energy to the system to make it go from a liquid to a gas. The enthalpy of condensation is the opposite, right? You go from a gas to a liquid, and that'll be the enthalpy of condensation, which will just be negative the enthalpy of vaporization. It's the opposite, right? It'll just be exothermic. If you're cooling from, well, the temperature stays the same, but you're cooling from, you're removing energy as it goes from a gas to a liquid. That energy slows down, the energy you removed slows down the molecules, and now they're stuck in the liquid phase because the intermolecular forces keeps it together. Fusion, right? It goes from, I'll give an example with water again. Let's use a different color, makes it nice to look at, right? So in freezing and fusion, sort of they're the opposite. In freezing, you go from water in a liquid state to water in a solid state. And the enthalpy here of freezing just is a negative the enthalpy of fusion, FUS. And this will be exothermic because, again, you're going from liquid to a solid. You need to remove energy. And so in fusion, you're going from a solid to a liquid. And that's the enthalpy change. We call it the enthalpy of fusion. This is endothermic. You need to add energy to melt ice, for example. I'm writing this all for water, but this is for any substance that changes phases. But again, we use water most commonly, so why not use water as an example? Sublimation is sort of going from solid to a gas, skipping the liquid phase, right? So you're going from H2O solid all the way to H2O gas. In all of these cases, the temperature is not changing, right? You're just changing the state of matter. And so this was the enthalpy of sublimation. And again, you need to add energy to do that. So this should be endothermic. And then deposition would be the opposite. We're going from a gas all the way to a solid, skipping the liquid phase. And so the enthalpy of deposition is negative the enthalpy of sublimation. And this will be exothermic because you release energy. So those are all the different phase changes that can happen with their associated sort of enthalpy changes. As we mentioned, enthalpy is usually written in units of kilojoules per mole, right? All of these. So I'm not going to write that over again. Okay, so basically, as something changes phase, you need to either add energy to it or it releases energy as it changes phases, even if the temperature of it stays the same. And that comes in useful in biological systems. I'm looking at number 17 now, where we sweat, for example, and that helps us cool down. Why it helps us cool down? Well, water goes from a liquid state to a vapor state, right? And so we need to add energy to that water for it to change from liquid to a vapor, and that energy comes from our body temperature. So it takes the heat from our bodies and vaporizes, and so we become cooler in the process. So in very hot climates, like in Guyana, we can lose as much as 1.5 liters of water, of sweat, really, per day. And for this exercise, even though sweat's not pure water, it has other stuff in it, we're going to treat it as pure water, and we're going to calculate the amount of heat removed by evaporation, assuming that's the amount of heat that we actually lost. So the question is asking how much heat is required to evaporate 1.5 liters of water. Now we know the heat of vaporization of water. Does it give it? Yeah, they give it to us. It's 43.46 kilojoules per mole. So if we want to figure out the heat, we just need to figure out how much moles of water that is. They gave us the liters and also in kilograms. So the mass is 1.5 kilograms, or in grams, that's 1,500 grams. If we can figure out the moles, then we can figure out the heat, right? So the number of moles is going to be 1,500 grams of water divided by the molar mass of water, which is 18.02 grams per mole. It's oxygen, which is 16, plus 2 times hydrogen, which is 1.01, so that's 18.02. So this should give us, let's see, to my page here, you hear my page turn, I'm not going to edit that out. It's about 83 moles to 2 sig figs. So we know the number of moles, we know the enthalpy of vaporization, so the heat that we get, or rather it takes away from us, is going to be 43.46 kilojoules per mole multiplied by 83 moles. So the heat there is Q, remember, is for heat. I punch this in my calculator, I get 3600 kilojoules of heat. That's a lot of heat that it's taken away. Okay, try number 18 on your own. Pause the video and then when we come back, we can work it out together. So we have 100 grams of liquid ammonia and it's boiling at its boiling point. So the temperature again doesn't change. And the enthalpy of vaporization is 4.8 kilojoules per mole. So in order to figure out how much heat is required, we need to figure out how much number of moles this is. So number of moles is going to be the 100.0 grams divided by the molar mass of ammonia. Nitrogen, I believe, is 14.01. Hydrogen is 1.01 grams per mole for the atomic masses. So this 14, I think this is 17.04 grams per mole. So if I plug this in my calculator, I get 5.869 moles, 4 sig figs. So the heat, Q, will be the 4.8 kilojoules per mole multiplied by the 5.869 moles, which gives me 28 kilojoules to 2 sig figs. Okay. So we know that things can go from solids to liquids to gases, and water is a substance that we look at often, can go from solid to liquids to gases. And then we also know that we need to add heat to also raise temperatures, right? We looked at this equation a while ago where the heat change is going to be equal to the mass times the specific heat capacity of the substance times the temperature change. So by doing that, we can actually track how much heat is added to any system as it goes from, let's say, a solid through a liquid through a gas, through heat changes from this equation, and also heat changes from the different vaporization or freezing or whatever process is going through. And by considering all of those things, we can set up what we call a heating curve for a substance. And this is the example for water. So as along the x-axis here would be us trying to add heat to the system. And on the y-axis is the temperature of the system. So let's say you're starting with ice at 10 degrees Celsius. As you add the heat, the temperature will change, right? In fact, the temperature will change according to this equation. You're adding heat, and so the temperature will change according to this equation. The specific heat capacity of ice, right? So the specific heat capacity of ice is 2.09 joules per gram per degree Celsius. Then, if this is at atmospheric pressure, you'll hit 0 degrees Celsius, where you'll add heat to the system, but the temperature doesn't change because that heat goes to melting the ice, right? And so that heat comes from equations like this. In fact, melting the ice will be the enthalpy of fusion, right? And the enthalpy of fusion is 6.01 kilojoules per mole. Let's put all of these in nice little square brackets so we remember what we need to use. Okay, and then all of the ice will be melted, and so as you start to add more heat, the temperature starts to increase again. All right, let's go orange this time. So the temperature will increase again. You add more heat, the temperature will increase again using the specific heat capacity equation, and we know that the specific heat capacity of liquid water is this one we used a lot, 4.18 joules per gram per degrees Celsius. And so we add more heat, the water will increase in temperature until we get to the boiling point. And then at that point, as we add more heat, let's use purple. As we add more heat, all that heat is now not changing the temperature, but changing it from a liquid to a gas. So that will be the enthalpy of vaporization, which we said was, what did we say it was? 43.46. No, I think it is 40.67. You may have to look this up, but 40.67 joules, kilojoules per mole, right? The enthalpy of vaporization. Okay, and then after you've added enough heat to vaporize all of the liquid molecules, everything is now in the gas phase, and so any additional heat will keep raising the temperature what, let's use green. Did we use green before? No, let's use green for this one. And so the specific heat capacity of steam really is what it is, right? Water vapor is, I believe, what is it? Let's see. Oh, 1.84 joules per gram per degree Celsius. So there is where all of your heat goes. First, if it's ice, it goes to raising the temperature of ice. Then it starts to melt the ice. Then it starts to raise the temperature of water. Then it starts to vaporize the water. Then it starts to raise the temperature of steam. Or you can go backwards, and it's a reverse process. So that all of those is what constitutes what we call the heating curve for water. Every substance will have a similar heating curve with different sort of values. Okay, so let's use these ideas in some questions. For example, let's look at number 19. It says that you have 135 grams of ice starting at negative 15 degrees Celsius. How much heat do you need to add it to convert it from negative 15 degrees Celsius of ice all the way to water vapor at 120 degrees Celsius? So let's look at the various different processes involved here. So the overall heat, right, will be equal to, first we need to raise the temperature of ice. So we use red for that one. So we'll call it Q from, let's call it raise ice temp. Okay, then we need to melt the temperature of ice. We use blue for that one, so it's the heat from melting. Then we need to raise the temperature of water. That was orange, so it's Q from raise water temp, so that's liquid water. And then we need to vaporize the water. That was purple, so that's the heat from vaporization. And then finally we need to raise the temperature of steam, Q raise steam temp. So in this problem, we have 1, 2, 3, 4, 5 different processes happening all throughout the sort of process. So let's start with it one by one. To raise the temperature of water, we use, raise the temperature of the ice, we use the specific heat capacity of ice, and the mass is 135 grams times 2.09 joules per gram per degree Celsius, such that grams will cancel out, times the temperature change. We're going from negative 15 degrees Celsius to the melting temperature, which is 0 degrees Celsius. So the temperature change there is 15 degrees, right? This is times 15 degrees Celsius, so degrees Celsius cancel out. And this will give us, I think 4230 joules, right? Now let's look at the next part, the melting of the ice to form water. Here we use the heat of fusion, which is 6.01 kilojoules per mole. So that means we need the number of moles. So let's calculate number of moles. We have how many? Let's see. Already forgot how much. What's the mass we're dealing with? 135. There we go. 135 grams of water. 18.02 grams per mole is the molar mass. And so we're dealing with, I believe, 7.49 moles. Okay, so we have 7.49 moles times the heat of fusion, which is 6.01 kilojoules per mole. So we end up with, this comes out to be kilojoules, and I believe this is 45.0 kilojoules. Okay, now let's deal with heating the water from 0 degrees to 100 degrees, right? Because that's this whole process here. So the mass is 135 grams, specific heat capacity is 4.18 joules per gram per degree Celsius, and the temperature changes 100 degrees Celsius from 0 to 100. So this all comes out to be, I believe, 56500 joules. Now we need to deal with the vaporization part, right? Again, we know the moles is 7.49 moles. The enthalpy of vaporization here was 40.67 kilojoules per mole. So this answer comes out to be in kilojoules. Let's see. I think it's 305 kilojoules. Okay, and then finally the green step, which is raising the temperature of steam, right? We're going from 100 to 120 degrees Celsius. The mass is, there we go, 135 grams. Specific heat capacity of steam, I believe, was 1.84 joules per gram per degree Celsius. So that grams cancel out. And again, the temperature change is 20 degrees Celsius because we're going from 100 to 120. So this all comes out to be in joules. I believe it's 4970 joules. To add this all up, we'll just convert everything to kilojoules, right? And so if I add it up, it's all 416 kilojoules, right? This is 4.2 kilojoules, this is 45, this is 56.5 kilojoules, 305 kilojoules, and 4.97 kilojoules. All right, so it's a lot of steps, but we got there, right? We raise the temperature of ice, we melt the ice. We raise the temperature of water, we vaporize the water, we raise the temperature of the steam. Try to do number 20 on your own. Same process, it'll take a while maybe, but try to do number 20 on your own. Okay, let's look at number 20. We have 94.0 grams for water. Let's just find number of moles right away because we know that we'll need number of moles. We divide it by 18.02 grams per mole, and I believe I end up with 5.22 moles. Okay, we're starting at 80 degrees Celsius and we want to cool it all the way down to ice at minus 30 degrees Celsius. So this is not as complicated, right? We're starting with water, so we don't have to deal with vaporization and steaming. So we start with water somewhere here, we need to cool it down, and then we need to form ice, and then we need to cool the ice down. So there's just 3 steps, right? First, so the overall heat would be equal to orange. It will be the heat from cooling water. Then we need to freeze the water. Which color did I use for freezing? Blue. Then we need to freeze the water, so heat from freezing. And then we need to cool the ice, and the color I used for that was red. So heat from cooling ice. All right, let's work with each of these one at a time. So for cooling water, we take the mass, 94.0 grams, times the specific heat capacity of water, times the temperature change, right? We're going from 80 degrees to 0. The final is 0, the initial is 80, so the temperature change is negative 80. Negative 80 degrees Celsius. That comes out, I believe that comes out to negative 31400 joules. Okay, now let's look at the freezing part. Freezing, the enthalpy change is 60.01 kilojoules per mole for fusion. Remember, freezing is the negative of that. So, where are we? Negative, I already forgot what it was, 6.01 kilojoules per mole times number of moles, I said was 5.22 moles. So I believe this comes out to be negative 31.4 kilojoules. And then now we need to cool the ice, right? So the mass is 94.0 grams times the specific heat capacity of ice is up here, 2.09 joules per gram per degree Celsius. It's 2.09 joules per grams per degree Celsius times the temperature change. What is our temperature change? We're going all the way down to negative 30 degrees Celsius. So we're going from 0 to negative 30. Temperature change is negative 30 degrees Celsius. So this comes out to be negative 5.89, I believe 5.89 kilojoules. Let me just run this by my calculator. 94 times 2.09 times 30. Yeah, it comes out to be 5893.8 joules or 5.89 kilojoules to 3 sig figs. So if I wanted to write this in kilojoules, it would be 31.4 kilojoules. This one right here. There we go. So now everything's in kilojoules, so we can just add them up together. And if I do, I get 68.7 kilojoules. Negative, right, because it's releasing heat, but the question is only asking for total amount of heat released. So we don't, they know the heat is already released, so we don't need to tell them by putting the negative sign there. All right, so that will bring us to the end of this video. And look at that, I did not stop at all. I don't know how much I stumbled, but let's summarize what we did. We did a lot of stuff. We talked about phase transitions. Phase transitions simply means changing the state of matter from solids to liquids to gas, or back to liquids or solids. We talked about vapor pressure. It's the pressure of a gas above its liquid, and that happens because even though something might not be at a high enough temperature to boil, there's still going to be some amount of molecules with enough temperature to escape, right? Because it has everything has a spread of kinetic energy. We talked about how that minimum kinetic energy is related to the intermolecular forces. The weaker the forces, the higher the vapor pressure, because more molecules would have enough energy to break those weak intermolecular forces. And so we can figure out at least whether something's going to have higher or lower vapor pressure based off of their intermolecular forces. So we did some of those, and we talked about how the boiling point happens when the vapor pressure is the same as the atmospheric pressure. We know atmospheric pressure at sea level, where we are in Indiana, pretty much sea level, is 101 kilopascals, but then it can vary with elevation. We looked at these different curves that show the vapor pressure as a function of temperature, and we see that they go sort of these curves, and we said that it's hard to estimate what the vapor pressure is at different temperatures just by looking at this curve. So to do it more accurately, we looked at the Classius-Clapeyron equation, where that curve is an exponential, so we can use an exponential to describe what's happening there. The pressure is related to some constant times the exponential of the heat of vaporization divided by R times T. R should be in this energy form, joules per mole per Kelvin, and temperature should always be in Kelvin. Then we derive this 2-point form all the way over here. Maybe you skipped it, that's fine. You don't need to know how to derive it necessarily, just how to use it, but this is a 2-point form. 2-point form means if we have two different pressures or two different temperatures, basically two different conditions that we want to explore, we use the 2-point format for the Classius-Clapeyron equation. So we use that to find a number of things. We can find the heat of vaporization if we know two different temperatures, two different vapor pressures at two different temperatures. We can find final temperatures at which things would boil if we know the heat of vaporization and some other quantities, or we can find vapor pressures using this equation at different temperatures. Okay, and then finally we look at different sort of enthalpies or various phase changes, right? Here's all of the different ones we looked at. And then we looked at the heating curve of water, which basically tells us how the temperature changes as we add more heat. Sometimes the temperature doesn't change when we add heat, and that's because all of the heat that we add goes to not raising the temperature, but rather changing the phase, either from a solid to a liquid or a liquid to a gas. And we did some calculations involving that. In our next video, we're going to look at phase diagrams. Fun stuff. I'll see you then. Bye.